Hello and welcome back to Jog Vlogs. This session is going to be continuing with the rivers topic. And last session, while we were looking at the causes and effects of river flooding, today we're going to kind of continue that theme and we're going to look at flood or storm hydrographs, which sound like an evil plot from some kind of Bond film, but they're not. They are a type of graph that we use to help us in predicting and managing floods. So you're going to learn about how they're constructed and what the little bits and bobs of them are, as well as getting a few notes down. And then you're going to be understanding how different things that occur within a drainage basin can actually affect what happens to a storm hydrograph. So once you've got the title written down, unpause and you can crack on. So this is a storm hydrograph. It looks a bit complex and it's got a couple of elements to it, and this looks far more complex than they would be in reality, because this one's labelled, and it's labelled to try and give you the overview of everything that's involved. So I'm not going to dwell on this too much because I'm going to take it bit by bit for you, but just to show you that after any rainstorm or rainfall event, it leads to the discharge or the flow of water in a river getting higher. That's pretty logical. More rain comes out of the sky, it will work its way to the river, that river will go up, or that river will increase its amount of water, its volume of water going past every second. So this is a graph which measures not only the rainfall event, but also what happens to the river after a rainfall event, and we call it a flood or a storm hydrograph, because essentially anything above the normal river level or base flow is classed as storm flow. So it's essentially, it doesn't mean it's going to flood, but it can lead to flooding if your capacity of your river is not very high. So let's do it bit by bit, and as I'm doing it, I'd like you to dedicate at least half a page really to sketch maybe this, the section I'm doing. So the first thing is you want your axes, and there's axes along the bottom, okay, is all about time. It might say hours from the start of the rainstorm, it might say days, whatever it does, okay, it's about time. So the x-axis is all time, and the y-axis, okay, has the outside axis anyway is discharge. Now discharge is how much water passes a certain point of the river every second, and we measure that river in terms of its volume. So volume is measured in things like meters cubed. So meters cubed per second is what we actually measure rivers in. So imagine you're standing at the side of a river, okay, and you're watching it flow from left to right in front of you. How many meters cubed worth of that water, picture that, a meter by meter by meter full of water, box that much, how much of that passes every second from where you're sitting? That's the discharge, okay? We sometimes call it cumex, cubic meters per second. But you'll also notice on here there's a tiny little extra graph, and this extra little graph has its own little axis, and this axis is measuring it in millimeters. Okay, so it's measuring rainfall, because rainfall is measured in millimeters, how far up a rain gauge it goes. So this rainfall event, you can see, after about, 3 to 6 hours, produced just under 2 millimeters of rainfall. In the next 3 hour spell, it produced just over 4, and then it slowed down to produce 2 for the final set of 3 hours. So this is like a rain event that lasted 9 hours. That's quite a lot. Although it didn't really lead to very much rain. 2 millimeters, 4, but it's not a huge amount. But this is the rain event that we want to document. We can't just use the discharge axis because this is nothing to do with water in the river at this point. This is water coming out of the sky. Okay, so we have to have this extra little axis. So pause the screen while you do a little quick sketch of this, please. And then when you're ready, unpause the screen and we can start to add the next element. Okay, so now you've got a sketch of this particular part or starting point of the storm hydrograph. I'd like you to now add this line. It's not the best of lines, truth be told. This probably shouldn't go down before it goes up. So this probably should be a bit of a straight line, but it should have a steep curve, a little dot at the top. That's just to help you identify something, and then another curve that comes down and slowly decreases. So try and get the overall shape of this particular line on your graph. Now what this line is, this represents the discharge. So this is now looking at this big axis. So you can see before the rain event the discharge was about 1 cubic meter per second, and then after the rain event it went up slowly. Okay, it rose, the discharge rose, the amount of water passing per second increased. Actually it peaked just over 3 cubic meters per second, and that took, well, from the start of the peak of the rainfall event to the peak of the discharge took about 12 to 16 hours, 15 hours, something like that. So that's useful information. But what you're also going to do is you're going to add extra labels onto your graph. So once you've done this line, we're going to just add these labels on, and I'm hoping that you can work out where most of these labels go. So peak rainfall is where the rainfall was its highest. Peak rainfall is here, the top bar, okay, the highest bar. Peak discharge, which we know this line represents, is right here. Peak rainfall, peak discharge. The rising limb, okay, sounds pretty gross, but the rising limb is the discharge as it increases towards the peak discharge. And then the falling limb is the on its way down again. Lag time is an important idea because it's very, very important for us to recognise how long it takes the amount of water coming out of the sky to show up in the river. And the reason that's important is because it tells us how long we're going to have. Because if we know our river floods, if it gets past, 2 cumex, then we know that this river is going to flood. And we also know how long we're going to have before it floods, and then how long it's going to take before it actually comes back down again. So anything over 2 cumex is going to be a river in flood, and we know that it's going to take 6 hours, maybe 9 hours before it's going to flood. And we also work out after the rain event how long it'll take before it gets below 2 cumex again. So you could have flooding for a period here of a full day, 12, 24, 48 hours maybe. Now, often over time, this is probably a bit longer, and flooding takes a while to subside if it's a really big rain event, but this isn't a particularly big rain event. So your labelling should look a bit like this. Now, I haven't put on base flow for you, but I've just added that now. Base flow is kind of a general flow that the river normally kind of has all the time. Storm flow is anything above base flow. Doesn't mean it's flooding, okay, just means it's what we call storm flow. The lag time is that distance between the peak discharge and the peak rainfall, because that's really important for us to understand. Okay, so just check your graph along this one to make sure you've got all the labels in the right places, and you understand where each of them goes and why. Pause the screen while you do that, and then when you're ready, unpause and I'll talk you through it. So, they're useful, and the most useful aspect is probably the lag time. And the reason that the lag time is the most useful aspect is because that is the aspect which gives us the opportunity for a warning to take place. Okay, so the warning taking place gives us that time to prepare our home and prepare what we're doing with regards to maybe flood protection and flood management. So if we have any ability to control anything about a river and to prevent flooding, the most important thing really we can try and do is increase the lag time. Now, what effect that will have in a river is it will allow the river the chance to deal with the water over a longer period of time. Now, if I could give you an analogy to kind of help you with this, if I gave someone like a jug of water to drink and I gave them 3 hours to drink it, they've probably got like a really easy task on their hands, because they can just sit and have a gulp now and then, and before you know it, over 3 hours the jug's going to be gone, no problem. If I gave them 3 seconds to drink that jug of water, it's going to spill out of their mouths while they're trying to, because they cannot physically deal with that volume of liquid in one go. Rivers are the same. If they have to deal with a big volume of liquid in a very short space of time, it will spill out over the sides. They will flood. It will burst its banks. But if that same amount of liquid is dealt with over a longer period of time, then the river won't flood, it won't burst its banks, and it won't lead to a flood event. Now you could ask, well, how on earth can you stop or slow down the water from reaching the river? But there are a number of ways that we can do that. And when you think of a river as not just one thing, it's part of a drainage basin, it's part of a whole area. There are things that we can do in that area which will slow down the rain and slow down the precipitation from actually getting to the river. And we can do it in a way that really allows that river to deal with the water that it's trying to process. So there are two. Hang on, let's just unclick on the screen. And that's just essentially what I've mentioned. There are two rainfall events, or sorry, the same rainfall event, sorry, I should say here. Okay, and this is a handout on 365. You need to find this, but you could just use this slide if you are struggling. Now, what the difference between these two is actually visible in the discharge. Okay, so these are two storm hydrographs, where actually rather than the rainfall being here, the rainfall's on the right hand side. But you've got the rainfall event, that's the same in both, and you've got this, which is your discharge. And the discharge looks very different, despite it being the same rainfall event, the same size, the same peak rainfall, the period of time is the same. So what is different about this drainage basin to this drainage basin? Why is it that this one has a shorter lag time and a higher discharge, whereas this one has a much longer lag time? You're looking at 60, nearly 60 hours of lag time, whereas this one, the lag time is 20 hours. Far longer for that river to deal with that same volume of water over the course of time. So to help you kind of show your understanding of what changes lag time, I've actually produced these things called most likely statements. So under each under each hydrograph, not paragraph, storm hydrograph, I would like you to write the statement which is most likely to be represented by that storm hydrograph. I'm not explaining myself very well there, so I'll do it again in a separate in another way. Drainage basin A here, drainage basin B here, lag time shorter, lag time longer. These, there's not 20, there's like 15. These 15 statements, okay, represent one situation that you would find in a drainage basin. So this urban area, that's what we mean by an urban area is a place with lots of concrete, a big town or a big city or a large town or city area. So places like London, Birmingham, Manchester, big urban areas that make up quite a big chunk of a drainage basin. Okay, are you more likely to find an urban area responsible for the storm hydrograph of drainage basin A or drainage basin B? It's one or the other. Now, an urban area is more likely to be drainage basin A. And the reason? Because urban areas have concrete, they have storm drains, they have impermeable surfaces. All of that means that water runs off the surface or gets put into the river very quickly. That is going to increase the discharge because it decreases the lag time. We are creating, the perfect conditions for water to go straight in the river. We're not slowing it down at all. So underneath drainage basin A, I would write urban area, or most likely urban area. Under drainage basin B, I would then probably write most likely rural area. Rural area, lots of countryside, probably lots of grass, trees, plants, lots of things which intercept the rainfall and maybe utilise it and absorb it from the soil. So all of that for the same rainfall event means that moisture is slowed right down and it creates a longer lag time. So this one, concrete, drains, short lag time. This one, grass, fields, trees, very long lag time. And that's what is most likely to be the case with regards to a rural area. So going through each of the rest of these, one of them is most likely to be a steep-sided valley or a place with steep-sided valleys. One of them is most likely to be a place with gently sloping valleys. One of them, area of forest, deforestation, etc. I'd like you to try and figure out which one belongs to which drainage basin and why. Okay, the important thing is why. Being able to explain why one of them belongs to A rather than B or vice versa is really, really important. Okay, so pause the screen, go through all of these, and then when you're ready, unpause the screen and I will give you the answers to those. Okay, so hopefully you've now got a list of most likely statements under drainage basin A and a list of most likely under drainage basin B. I've already done the urban and rural area ones and explained those in my explanation of the task. I'm going to now go through the other ones. So, steep sided valley, most likely to be drainage basin A because there's less infiltration, the water slides off the slopes quicker, leading to a shorter lag time. A gently sloping valley, for the opposite reasons, is most likely to be drainage basin B. Area of forest, most likely to be drainage basin B, again because forest intercepts the rainfall, increases lag time. An area of deforestation, for the opposite reasons, most likely to be A. Impermeable rock type, like granite. Well, we know from last lesson that impermeable rock leads to flooding, so it's more likely that impermeable rock leads to more surface runoff, less infiltration, shorter lag time. A. Permeable rock, chalk, which absorbs moisture, can slow it right down through percolation. B. Frozen ground. A. Frozen ground acts like impermeable ground, and therefore water surface runoff occurs, shorter lag time. Uncompacted soil. B. Allows water to easily pass into it, slowing it down. Area with high monthly precipitation. This is a tricky one, and this one really probably should go under B. Unless it's not supposed to have high monthly precipitation. So the fact it says it's high monthly precipitation suggests that it always happens, which means that it's a place that's likely to normally have high monthly precipitation, so it's rivers that are used to it. But if it's an unusually amount of high precipitation, then it's going to be A. If it's a dry part of the country, I would say that's more likely to be A, because in a dry part of the country, you get more deposition in rivers because it's more drought. Therefore, the river's capacity is less, and the ground can be baked hard. So when you do get a rainfall event, it runs straight off, goes into the river quickly, lag time reduced. An area with heavy snowfall, likely to be A, lots of moisture, melting all at once. And a river with lots of sediment settled in the bed, also A, because it reduces the capacity of that river. B would be a river maybe that's been dredged for sediment, so it's maintaining its capacity for much of the time. Okay, I think, I hope that concludes sufficiently, and you've got a good range of answers written down, and you understand now what storm hydrographs do, how they work, and how they can be really useful to us, particularly with this lag time, but also the conditions which can affect those storm hydrographs. Okay, that concludes this session, other than to provide you with a homework task, which I'll explain very shortly. Okay, so to help really recap on the last session, which we looked at when it came to command words and making sure you're accessing as many marks as possible from quite tricky kind of explain style questions, I've actually got a bit of practice for you to do. Now, it says homework on here, but as you're doing this from home already, don't view it as homework. This is just really very good and useful exam practice for you to utilise. What I'd like you to do is try and answer this question. So outline, which really just means the same as explain or suggest reasons. Outline one human action that can lead to river flooding. So this really is nothing to do with storm hydrographs. This is just recapping on the last session that we looked at, which was the causes of river flooding. I really want you to try and see if you can get all four of those marks. So outline wants you to link your answer back to the question, you've got to name a human cause of river flooding, and you've got to explain in multiple steps how that leads to river flooding. Okay, so try and do it with extension. Try and make sure you're incorporating key terms like surface runoff, infiltration, interception if needed, and see how you go. All right, and if you want to submit that to me, please feel free. You can email it or just bring it into next lesson when you come in. All right, that finalises this session on storm hydrographs with a bit of exam practice thrown in too. Thank you very much for listening, and I'll see you next time.